Hey everyone, welcome to another exciting episode where we simplify complex machine learning concepts. Today we are tackling a topic that's super important and incredibly useful, that is logistic regression. Whether you are predicting if an email is spam, diagnosing diseases, or even determining if a customer will buy a product or not, regression is one of those go-to tools you need in your toolkit. It's simple, effective, and widely used in real world applications. In this video, I am not only going to explain what logistic regression is, but also how it works behind the scenes and how you can implement it in Python. Plus, we'll discuss some real world use cases where logistic regression shines. So, if you ever been curious about how to predict yes no outcomes with machine learning, this video is for you. Let's get started. Here's the roadmap for what we will cover in this video. First, we'll understand the concept of regression and why it's important. Second, we'll dive into what logistic regression really is and how it differs from linear regression. Third, I'll break down the math behind logistic regression and explain the sigmoid function. Fourth, we will compare linear regression and logistic regression to understand their differences. Fifth, we will explore some cool and real world applications of logistic regression. Sixth, finally, we will implement it in Python and evaluate its performance on a dataset. By the end of this video, you will be well equipped to use logistic regression in your own projects. Let's start with the basics. Regression. Imagine you are trying to predict how much a house will sell for based on its size, number of bedrooms, and location. That's classic regression problem where the output is a continuous value. In this case, the price of the house is a continuous value. Regression helps us understand the relationship between the dependent variable, the thing you want to predict, and the independent variable, that is the factor that influences the prediction. For house prices, the independent variables might be square footage, number of bedrooms, or even proximity to schools. When we use linear regression, we assume that there's a linear relationship between the input features and the output. For example, we might assume that as square footage increases, the price also increases linearly with it. But what if we aren't predicting a continuous value like house prices? What if we need to predict a categorical outcome? For example, whether an email is spam or not. That's where logistic regression comes into play. Now, what is logistic regression? Logistic regression may have the word regression in it, but don't let that fool you. It's actually used for classification problems where the goal is to predict a binary outcome. You will often use it to predict something like yes, no, 0, 1, or true, false. For example, will a customer buy a product or not? Does a patient have a particular disease or not? Or will a student pass or fail in a course? The key idea in logistic regression is that instead of predicting a continuous value, it predicts the probability of an event. The output is always a probability between 0 and 1, and based on these probability, we can classify the outcome as either class 0 or class 1. For instance, if our logistic regression model predicts that there's a 0.9 probability or 90% chance that a customer will buy a product, we will classify that as a yes. If the probability was lower, say 0.2, we would classify it as a no. Now, let's dig into the math behind the logistic regression. Don't worry, I'll keep it intuitive. In linear regression, the model is based on the equation of a line, that is, z is equals to b0 plus b1x, where z is the dependent variable, x is the independent variable, and b0 and b1 are the intercept and slope respectively. This works well when predicting continuous values, but in logistic regression, we don't want an output that can range from negative infinity to positive infinity. Instead, We need an output between 0 and 1, which represents a probability. So, to convert these linear output into a probability, we use the logistic function, also known as sigmoid function. This function takes any real value number and maps it to a value between 0 and 1. The logistic function is given by p y is equals to 1 x is equals to 1 upon 1 plus e to the power minus z, where py is equals to 1x is the probability that the output y is equals to 1 given the input x, where z is equals to b naught plus b1x. E is the base of the natural logarithm. E to the power minus z ensures the output is between 0 and 1. Now plug in the linear expression for z into the logistic function. Py is equals to 1x is equals to 1 upon 1 plus e to the power minus b naught plus b1x. This is the logistic regression equation that gives the probability of y is equals to 1 for a given value of x. The term b naught plus b1x is the linear combination of the feature, just like in linear regression. But applying the logistic function ensures that the output is a valid probability. How it works? When z is equals to b naught plus b1x is a large positive number, e to the power minus z becomes very small, making the probability close to 1. When z is equals to b naught plus b1x is a large negative number, e to the power minus z become large, making the probability close to 0. When z is equals to b naught plus b1x is equals to 0, the probability is 0.5, meaning the model is unsure and treats the outcome as equally likely. This equation is the foundation of logistic regression and allows us to predict probabilities for binary outcomes. The cool thing about the sigmoid function is that it maps any input values, whether large positive or negative, to a probability between 0 and 1. Now, checking the model accuracy in logistic regression. Once we have trained our logistic regression model, it's crucial to evaluate how well it performs. We can measure its accuracy using a few key metrics. That is, first, accuracy score. The accuracy score is the simplest metric. It tells us the percentage of correct predictions out of all predictions. Second is confusion matrix. Confusion matrix gives a detailed breakdown of the model's performance by showing how many instances were correctly or incorrectly classified for each class. It has 4 components, that is, first, true positive. Model correctly predicts 1. It's a positive class. Second, true negative. Model correctly predicts 0. It's a negative class. Third, false positive. Models incorrectly predicts 1 when the actual value is 0. It's also known as type 1 error. Next is false negative. Model incorrectly predicts 0 when the actual value is 1, also called as type 2 error. Third, precision, recall and F1 score. To dig deeper, we can use precision, recall and the F1 score. Precision. Out of all positive predictions, how many were actually correct? That's a precision. Recall. Out of all the actual positives, how many did we correctly predict? F1 score. A balance between precision and recall, especially useful when you have an imbalanced dataset. Now, let's see the difference between linear versus logistic regression. We are going to compare linear regression and logistic regression to clarify when to use each. First, linear regression predicts a continuous value. For example, it might predict a house prices like $250,000. Logistic regression predicts a probability, which is then classified as either 0 or 1. For example, it might predict a 75% chances that a student passes, which we classify as a pass. Second, linear regression uses a straight line equation, where logistic regression uses the sigmoid function to squash the output into the probability between 0 and 1. Third, linear regression is used for regression problems where the goal is to predict a continuous variable. Whereas logistic regression is used for classification problem where the goal is to predict a category like yes, no, or spam or not spam. The main takeaway: use linear regression for continuous outcomes and logistic regression when you are dealing with category. Where can you apply logistic regression? Here are some cool real world use cases. First, medical diagnosis. Predict whether a patient has a disease based on their symptoms and medical history. Logistic regression can predict the probability of having the disease. Second, spam detection. Classify whether an email is spam or not by analyzing features like the email's content, sender, and the subject line. Third, credit scoring. Predict whether a loan applicant is likely to default based on their financial history, income, and credit score. Fourth, marketing campaigns. Predict whether a customer will respond to a marketing campaign, helping businesses allocate resources efficiently. Fifth, fraud detection. Identify whether a financial transaction is likely to be fraudulent based on patterns in transaction data. It's widely used in areas like healthcare, finance, and marketing, where binary outcomes are crucial for decision making. Now that we understand the theory, let's dive into the practical implementation of logistic regression using Python. We'll use a real world data set to predict whether or not a person has diabetes based on several health parameters. So let's open Colab and do it together. First, we need to import all the required libraries. I'm importing pandas, then importing NumPy, then from sklearn.model selection, I'm importing train test split to split the dataset into training part and testing part. Next, importing our model, that is logistic regression. Then importing accuracy score and confusion matrix from sklearn.metrics. Run this. Okay, it's done. Next, upload the dataset. Inputting the path of the dataset. Then data.head. It will show the first 5 rows of our dataset. So here's the dataset look like this. It has column named pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, age, and outcome is our target value. Next, I will show how many rows and columns it has using data.shape. You can see it has 768 rows and 9 columns. Now, before we train model, we need to split data set into features. Run this. Now we are ready to run our logistic regression model. We are using logistic regression class from scikit-learn. Giving max iter as 200. It ensures model converges. It's an optimization process. Then model.fit. And this. Okay, once it's trained, we are going to evaluate the performance. Let's check accuracy. Then print the accuracy. And print confusion matrix. Next, run this. You can see the accuracy of our model is 0.35, which is not that bad. And you can see here the confusion matrix. Okay, so that's a wrap for today's deep dive into logistic regression. We covered everything from understanding regression, the logistic function, and the differences between linear and logistic regression to real world use cases and practical implementation. I hope you find this video helpful. If you did, make sure to hit that like button and subscribe for more content like this. Thanks for watching, and I will see you in the next video.